We will start with Yuehao Bai first. Yuehao is now a graduate from Chicago, now is at Michigan.
Okay, thank you, Xiaohong. And I will share my screen. All right. Can you guys see it?
Yes.
All right, thank you. So I'm very glad to talk about my paper. The title is Optimality of Match Pair Designs in Randomized Controlled Trials. So as you could see from the title, this paper studies the design of randomized controlled trials, or RCTs. And RCT has been pretty common in economics. So if you go to the AEA RCT registry, this is a place where people pre-register their experiments before running them. You can find about 4,000 experiments. So this number has been growing very quickly. And today I'm going to focus on one of the popular strategies that is used in design of RCTs, which is called stratified randomization. So I will define it formally later, but just in a few words, stratified randomization, what you do is that you have some individuals or you have some units, and you partition them into different groups, or what's called strata here, based on their observed covariates. So for instance, you might have information on their gender, their age, their income, things like that. You can first partition them into different groups, and you can say, okay, let me randomly assign half of each group to treatment. Now, this particular strategy, stratified randomization, is also very common in RCTs. So you can find more than 600 experiments in the same registry that I've just mentioned. So there are a lot of reasons why people want to use stratification or stratified randomization, but one of the leading motivations is the following. So I just pick a quote from this book by Glenister and Takavaraja, trying to describe the intuition why you want to stratify. And this quote says the following. So if you consider an example, so an experiment where you want to study the effect of some educational program on test scores, let's say that. And before running an experiment, you have some information on the units or on the individuals. And let's say that information is a baseline test scores. So before running experiment, you have some baseline test score information on them. And now you have a decision to make. You can either just ignore that information or stratify those individuals according to that information. So you have basically two choices, let's say that. So what happens if you don't stratify according to the baseline test scores? So it may happen that actually when you run an experiment and you see the treated group and the control group, it may just be the case that most people in the treated group are those with high baseline test scores, while most people in the control group are those with low baseline test scores. Because you didn't stratify, there's no guarantee you're going to end up with balance. So if that happens, then when you take the difference between the average outcome in the treated group and the average outcome in the control group, and use that as a proxy or an estimate for the ATE or the average treatment effect, then, well, you might see a large difference, but you can't tell whether the difference is because of the baseline test score or because of the treatment or the educational program itself. So to summarize all the intuitions that I've just explained, one of the leading motivations for using stratification is what I call here reducing bias. And this bias is very particular because it is the bias after you have assigned treatment. So let's keep that in mind. I will formally define what this bias is in a second, but one of the leading motivations is to reduce this kind of bias. Okay, so let's suppose you decide on using stratification. Let's suppose that. But you still have a lot of choices to make. So for instance, you can decide on how many strata you want to have. For instance, if I give you 100 units, you can say, okay, let me just put them in 2 different strata. So each of them has, let's say, 50 units. Or you can say, let me put them into 50 different strata or something in between. So you have a choice to make there. That's the first thing. And second thing is that what kind of covariates do you want to use when you stratify those individuals? So let's say you have information on their gender, you can use gender. If you have information on age or income or all those kind of things, you can use a few of them or all of them or none of them, things like that. That's the second thing. But there's a third thing which is kind of subtler, which is whether you want to do matching or do you want to use a coarse partition of the individuals. So let's again go back to the example. Let's say you have, let's say you have the income of those individuals. You can say, let me just pick a cutoff, and all people below the cutoff is going to end up in one stratum, and all people above the cutoff are going to end up in another stratum. You can do that. That is a very coarse partition because you have only one cutoff. But you can also do matching. So by matching, I mean you just trying to match them into let's say pairs according to their information on income. So for instance, here you can just order them according to their income and pick the first two as a pair, second two as a pair, and so on and so on. This is a very fine partition, and this is called matching. So you can do that too. So you can already see that the choice set is very large, and the paper tried to ask, well, what is the optimal way to stratify among all of them? You can see, I mean, this thing is already getting out of control. So I have to make some restriction on the problem. But all the restrictions are motivated by empirical practice. And you can see, well, I'll explain in a second, they're not very restrictive at all. So the first thing I'm going to assume is that we're interested in the estimation of average treatment effect, or is the ATE. So this is the expected difference between the potential outcome if you're treated and the potential outcome if you're not treated. This is a parameter that I just keep fixed. And for today, I'm going to make an additional assumption, which is that within each stratum, not only across the whole sample, but also within each stratum, you assign half of the stratum to treatment. So when I say half, I mean exactly the half. So you impose that. Now, this thing can be relaxed in paper. So, but just for convenience today, I'm going to focus on the case where 1/2 of each stratum is assigned to treatment. So once you assume you're interested in ATE and you assign half of each stratum to treatment, it is very natural to just estimate this ATE by the difference in means estimator. So by difference in means, I mean you take the difference in the average outcomes of the treated and the control groups. So that is the estimator you're going to use. And the problem I'm going to consider today is the optimization is to choose a stratification in order to minimize the mean squared error of this difference in means estimator. So that I mean I want to maximize the precision in this given estimator by choosing over different stratifications. Of course, when I choose stratification, I have some information which are the observed covariates. So I want to use that information as well. This whole problem is very complicated to solve because it is basically combinatorial. So if I give you 100 units, I ask you to partition them into different groups. There are so many ways you can do that. So if you enumerate all kinds of partitions, it's going to take forever. But fortunately, I can show the solution is very simple, and the solution takes the form of a match pair design. So when I started the problem, I say the choice set can be anything. You can have a stratum of size 20, 10, 100. But actually, the optimal thing to do is a match pair design, which means that you only have 2 units within each stratum. So you have pairs, 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 and so on. And you assign one of each pair to treatment. And in particular, this match pair design is defined by a very simple function. So I'll explain what this function is in a second. But suppose I give you such a function. This function is a function of the covariates. And all you need to do, because it is one-dimensional, all you need to do is order the units according to the values of this function, and then you just pair the first 2 units, second 2 units, and so on and so on. And then you randomly assign half, or actually one of each pair to treatment. That's it. So actually, this function also is very intuitive. It is the expected outcome given the covariates. And by expected outcome, I have to be very careful because we're in an experiment. And you basically have 2 outcomes for each individual. You have the potential outcome if you're treated, potential outcome if you're not treated. And well, here we just simply weight them by 1/2 each. And if you take this weighted average, takes the conditional expectation given the covariates, that is the function that you want to use. So there's a huge literature on the design of experiments and everything related to my talk, but for the sake of time, I'm going to skip all of that. So let me formally introduce this first result that I just described. So in order to do that, I need to introduce some notation. So we have IID units, and they're indexed by 1 up to n. And for the IC unit, I have several quantities. First of all, I have some observed covariates when I design the experiment, and I call them xi. And then I have the treatment status of each unit or each individual, and I will denote that by di. once you run an experiment, you will see the observed outcome, which is called yi. And this yi is going to be a function of your treatment, which is di, but also two potential outcomes. So y1, which is potential outcome if you're treated, and y0, which is potential outcome if you're not treated. As I described before, our parameter of interest today is the average treatment effect, or the expected difference between yi1 and y0. And formally, a stratification is a partition. So if you have n units and their indices are 1 up to n, a stratification, which I denote by lowercase lambda, is just a partition of this set of indices. So by partition, I mean that there's a collection of sets and they have empty intersection. Their union is actually 1 up to n. I will use capital lambda to denote the set of all stratifications. Now, of course, once I stratify them, I still have a choice to make, which is how many or what is a fraction of each stratum that I want to assign to treatment. And that is denoted by tau s. As I said before, I'm going to focus on tau s equal to 1/2 today, but this thing can be relaxed in paper. The only obvious restriction that tau s equal to 1/2 today is going to make is this implies every stratum has an even size. So it can be size 2, 4, 6, or things like that, but I don't know how to assign half of 3 units into treatment. That's the only restriction that I need to make. All right. So because I assume the treated fraction is the same within each stratum, it is very natural to use the difference in means estimator, which is again simply just taking the difference between the average outcome of the treated group and the control group. So this is what I call theta hat. Now, a lot of people use other kinds of estimators in analyzing this kind of experiment. So for instance, sometimes people use this regression with straight-up fixed effects, which means that you regress your outcome on the treatment status and also a bunch of indicators for straight-up. Or sometimes people run those what's called fully saturated regression. So you regress y on D, and also a bunch of straight-up fixed effects, and also the full interaction between the straight-up fixed effects and your treatment indicator D. It turns out that in our current setup, because the treated fraction is the same within each stratum, all of those estimators are the same. So the theta hat difference in means is quite general. Okay, so the problem we want to consider again is to minimize the mean squared error. And this mean squared error is conditional on x. So x1 up to xn. And well, when I minimize the mean squared error, there's a dependence on your stratification. Well, it's not obvious, but if you look at it, your difference in means estimator depend on treatment status. And the distribution of treatment status is going to depend on your stratification. So if you think through that. Now, as a result, this expectation will depend on stratification. So what I will do is to minimize this conditional mean squared error given the information I have, which are the observed covariates x, by choosing over stratifications lambda. So I want to describe the reason why the match pair design is optimal. So for doing that, it is very helpful to distinguish between two different notions of bias in our case. So I will define them as ex-ante bias and ex-post bias. So as you can probably tell from their name, their only difference is because of additional layer of conditioning. So for ex-ante bias, I mean the bias of theta hat given x, which is observed covariates. But for ex-post bias, it is additionally conditioning on the observed, or actually the realized treatment status, which is denoted by dn here. So in words, ex-ante bias is before you have assigned treatment status, and ex-post bias is after you have assigned treatment status. So of course, ex-ante bias is averaging over all kinds of possible realized treatment status. And by the law of iterated expectation, you can see that the distribution of ex-post bias is actually centered around the ex-ante bias. So this is what I said here. Now, the reason why I want to introduce those two different notions of bias is to make it clear that if you are interested in the ex-ante bias, then you don't care about your choice of stratification at all. The reason is that ex-ante bias doesn't depend on stratification. So why? If you write down the difference in means estimator, if you calculate the ex-ante bias, you can write it down. You will see that ex-ante bias only depends on the marginal treatment probability of each unit. but the marginal treatment probability of each individual here is 1/2. And it doesn't change with stratification at all. So if you care about ex-ante bias only, then you don't need to care about the choice of stratification. But it's a different story for ex-post bias. So the distribution of ex-post bias actually does depend on stratification. And the reason is that, again, ex-post bias is a function of your realized treatment status. And the distribution of your realized treatment status D will depend on your stratification lambda. So the distribution of ex-post bias will in turn depend on lambda or your stratification. So to illustrate everything that I've just said, I plot the distribution of the biases for two different stratifications, one for the blue bar and one for the red bar. And you can see that both of them are centered around the same thing, which is the ex-ante bias, because as I've said, the ex-ante bias doesn't depend on stratification at all. They're the same. But the red bar is more spread out than the blue bar. And you can see the ex-post bias is more spread out. And intuitively, you can tell, well, this is a worse stratification, but we need to make everything formal here. That intuition is true. So this first element of the proof that I'm going to discuss is actually saying, if you want to minimize the mean squared error, you are equivalently just minimizing the second moment or the dispersion of this ex-post bias in this graph. So if you think about the minimizing mean squared error, they're equivalent to both of those things. It might be kind of awkward now because, well, one of them is minimizing the second moment, which is intuitively the size of ex-post bias, and the other is minimizing the variance or the dispersion of ex-post bias. But how can they be equivalent? And the reason is actually very simple, because if you think about variance, it's the expectation of it's the second moment minus first moment squared. If you substitute everything by the quantity we're discussing today, then the variance or the dispersion of ex-post bias is the second moment of ex-post bias minus first moment squared, which is really ex-ante bias squared. But ex-ante bias doesn't depend on stratification at all, so it is equivalent to minimize this dispersion and minimizing this the second moment. So this is the first thing that I want to mention. Now, to connect back to the quotes at the beginning of the talk, the quote is saying, okay, after you assign treatment, you might see a lot of people with high baseline test score ended up in the treated group. A lot of people with low baseline test score end up in the control group. That is conditional on one realized treatment. So the bias here you're thinking about is supposed to be the ex-post bias. So as I've said, minimizing mean squared error is actually minimizing the size of the ex-post bias. So the first element of the proof actually connects back to the intuition very well. That's the first element. The second element of the proof is the following. So if you think about the idea that I've just introduced, I say, okay, you can minimize mean squared error. You're equivalently minimizing second moment of ex-post bias or the dispersion of it. But it's not obvious this makes our life any easier because the choice set is still very large. We can have a stratum of stratification with stratum of size 4, 8, 100, things like that. But why is the optimal solution a match pair design? And the reason is the following. If you think about any kind of general stratification, let me take just 4 units now. So you have 1, 2, 3, 4 different units. Suppose you don't use match pair designs. You throw 4 of them together in one stratum. This is actually equivalent to implementing 3 different match pair designs with 1/3 probability each. So 1, 2, 3, 4 is equivalent to implementing 1, 2, and 3, 4. So that's one match pair design. Or 1, 3, and 2, 4. That's another match pair design. Or 1, 4, and 2, 3. That's another match pair design. So implementing all 3 match pair designs with 1/3 probability each, it is equivalent to implementing that. If you think about it, mixing cannot be better than the optimal pure strategy. And by pure strategy here, I mean a match pair design. So you don't need to search over all kinds of mixing or stratifications. You only need to focus on match pair designs. So to get to the results, we only need to combine the 2 elements of the proof. So first of all, you only need to consider pairs. And second of all, any match pair designs, for any match pair design, you only need to look at the dispersion of ex-post bias. If you carefully write down the expression of the dispersion of ex-post bias, So here I need to introduce another notation, but it's really just saying you can represent the match pair design by using a permutation. So let's say you have 1, 2, 3, 4, and you want to match 1, 3, and 2, 4. What you can do is to first permute 1, 2, 3, 4 into 1, 3, and 2, 4. And then you just match the first 2 and second 2. So first 2 is 1, 3, second 2 is 2, 4. And the dispersion of exposed bias is actually proportional to the sum of square difference in terms of a certain function g. Let's say I give you this function g for a second. And what I tell you to do is to match all those units into pairs, trying to minimize the sum of square difference in terms of this quantity g. What is the best thing you can do? The best thing you can do is to just line them up and take the first 2 as a pair, second 2 as a pair, and so on and so on. That's really the best thing you can do if you think over that. Otherwise, you're going to end up with redundant segments on the line. That's it. Now, this function g is actually, as I said, expected outcome given the covariance. So we have y1 plus y0 here. Because we only care about the ordering of g, not the absolute magnitude, you can stick in 1/2 here and 1/2 here, and it's really the expected outcome. So formally, everything I've just said about the segments is Hardy-Littlewood Poiseuille rearrangement inequality. Okay, so to summarize the results, it's really saying taking this function, you order them, line them up, and then you take the first 2 as a pair, g1, g5, second 2 as a pair. And to connect back to the literature, in the test score example, you have the baseline test scores. And you want to match people according to the expected outcome given this baseline test score. Well, it's not crazy to say that expected outcome because the expected outcome are n-line test scores. It's not crazy to say that expectation is an increasing function of the baseline test scores. As a result, I don't need to know the magnitude of g at all. I only need to know the ordering. So that's it. You can just match them according to the baseline test score. And everything can be connected back to literature. But I want to just briefly mention what I did in the rest of the paper. So of course, you can see that everything relies on this function g, which is in general unknown. What I did is that, well, fortunately, we often have access to those pilot experiments, and they're run for many different reasons, but we often have access to that data. If you have pilot data, you can try to make everything feasible. And I propose different feasible procedures based on the sample size of your pilot. So you may have a large pilot. In that case, you can just estimate this function g and match according to this estimate. You're going to do very well because you have a large pilot. And the important thing there is that I only require the L2 consistency of your estimator for this function g. I don't need any rate condition or uniform consistency or things like that. So you can use a lot of machine learning methods for it as well. When you have a small pilot, the story might be different because you can't use fancy estimation techniques anymore. Sample size is too small. But I still propose a penalized procedure, which is motivated by a Bayesian problem. And after that, I introduced inference methods for the ATE. And inference methods here is complicated because you have a large number of strata. There are dependence here and there. But I provide very computationally easy procedures for inference. And this extends the result in another paper with Joe Romano and Zimchik. And finally, I illustrate everything that I described. So I made everything feasible. I illustrated by running my own experiment. So what I did is that I take this paper by Delevania and Pope 2018. I take the same outcome as in their original paper. I take one of their treatment arms. And I just redesign the experiment using my proposed stratification. And I run an experiment on Turk. And I see the standard error actually decreases by 29%. So if you translate everything back to sample size, because the standard error really scales with the square root of sample size, this means in order to attain the same standard error, I only need half of the sample size. So this is everything I have for today, and thank you.
Great, you're perfect on time. And you got one question from Zara. Actually, he asked 2 questions. First one is on your slides 6 to 7.
Oh, I should probably
Sorry.
turn it back on. Yeah.
Yeah. What to do to generate match pairs if you care about multiple outcomes, such as in healthcare, we may care about
Yeah, that's a great question. So yeah, it is not very obvious what we can do in that case, because it depends on how you weight different outcomes. So one obvious answer that I can give is that suppose you are interested in a linear combination of multiple outcomes, then you can easily extend what I described here. But suppose you're interested in some other metric, then the solution is going to be different. I'm not sure what is the solution there, but yeah, thank you.
So that's for future work. The second question he asks is, how does this apply to cluster randomized trials, such as treatment applied to hospitals but outcome at patient level?
Yes, that's a great question as well. So actually, it's something we're thinking about right now, and cluster outcome is kind of more complicated because first of all, because of the dependence, we need to sort of rederive everything in the limiting framework. Well, that's a different problem. But also here, because if you have individual level data, but you're interested in a cluster level outcome, then sort of the setup is going to be different. And it's not obvious, you can summarize everything by using just, for instance, the average of within the cluster. So it's not obvious that's true. So we're still working on that, but I don't have a great answer for that now, but that's a great question. Yeah.
Good. So that Adam has a question. How sensitive are results to focus on pure differences in means estimator?
Yeah, that's a great question as well. So as I have said before, the difference in means is not very restrictive at all, because you can use a lot of different estimators and they collapse to the same one, which is difference in means here. And in general, I think the match pair design part of the result is very general. So because all the things relies on realizing the stratification is a mixing of match pair designs. So suppose you use a different kind of estimators, or maybe even a different kind of loss function, you can still get a match pair result. But if you use a different estimator or some different loss function, the optimal thing might be a match pair design, but it may well not be the match pair designs that I mentioned today. So it is going to be, well, the short answer is that it's going to depend on what estimator you want to use and what loss function you want to use.
Yeah. Okay, great. So, one more question.
Yeah.
Thanks for great presentation, interesting results. I have one question regarding how the results would differ if you took into account the attrition attrition.
Yes. Okay. That's also a great question. I guess the result there is going to depend on whether attrition is random, or it depends on things that you can observe in the data, or you can't observe in the data. So I'm not sure. So the short answer now is that I'm not sure what's going to happen. But we need to carefully sit down and write down a model for attrition in that case. But that is a great direction for future work as well. Thanks.
Yeah, great. Thanks for the great presentation, and thanks for all the interesting questions for future work.
Yeah, thank you. Yeah.
Yeah. So perfect timing as well. So let's now move to the second speaker. It's Julius, and he graduated from Madrid the third or Sanfei, and now is an assistant professor at University of Cambridge. Okay.
Thank you.
Yeah.
Thank you for having me, and thank you all for joining. So today we'll talk about network dependence, and in particular about the following 4 aspects, which come from multiple but very closely related papers. So I will be talking at a somewhat very high level to explain how they all are related. So first I will start with the network dependence framework that consists of 3 main parts, and with the key concept there being network stationarity. Then given this network stationarity concept, I will be able to show you some asymptotic theory results. Things like 2 laws of large numbers, consistency of the covariance, and the central limit theorem. Then given the framework and given the fact that we're working with network data, I will suggest a way how we may estimate something that I call network dependence counterfactuals. And lastly, I will propose an idea how in practice, we may be able to do better in a certain sense using machine learning. So let me start with this somewhat dense introductory slide that relates to all 4 aspects. So at the very beginning, I claimed that there is no single natural distance for socioeconomic networks. And by that, I mean that the shortest distance on the graph is not the single best thing to do, because, for instance, we may have 2 leaders in a network that may be mimicking each other, but actually to be very far away in terms of connections. So with this general motivation, then I propose this framework consisting of a network, then what I call a classifier, and the classifier is something similar to a very general distance. It doesn't have to be an actual distance, but it's a certain graph statistic for 2 vertices. And lastly, there's network stationarity, that is a very similar type of stationarity as in time series, as you will see. And this relates to, well, it relates to all kinds of network structures, dependent structures, and particularly it relates to latent space approach, where we say that 2 nodes are connected if they are sufficiently close in some latent space. Now, I don't have a latent space and I'm not interested in connections. What I will be interested in is covariance. Which pairs of entities have the same covariance? And I will not have a latent space. Instead, I will have some unknown, well, not unknown, but some general measure or distance. Then, as I said, given the framework, I will be able to show you a couple of laws of large numbers, consistency of autocovariance functions, and the central limit theorem. Then there's a bunch of papers on asymptotic theory with network data. And roughly the main difference there would be that I do not consider network formation model, and my assumptions are of a somewhat high level. Then a different idea motivating the network dependence counterfactuals is that a change in a network affects potentially everything, unlike in other dependent structures. And by that I mean, if we remove a single link, it may eliminate many paths, it may change the connectedness, let's say, significantly, while that is not the case in something like spatial data, where if we remove a single point, it doesn't really affect the pairwise relationships. So given this observation and given the framework, in particular, given the network stationarity concept, I propose a way how we may estimate the counterfactual covariance between outcomes of 2 entities of a graph, of a network, under a given hypothetical network structure. And one thing, what this relates to is counterfactual distributions, and it relates in the sense that both of those are somewhat high dimensional, not just as counterfactual mean, but again, the similarity is not that close. And lastly, this distance that I call a classifier, in practice, we may choose something explicit, as I will give examples, like still the length of a shortest path. And such manual specified classifiers or distances are likely to be too restrictive to actually capture those complex patterns of network dependence. But then on the other hand, graph embeddings allow to map pairs of vertices to spaces where I am able to cluster those pairs of vertices. And the fact that I am working with pairs of vertices rather than with single vertices, as you see, makes a big difference. So given this idea, given the fact how graph embeddings work, it suggests that we may want to use machine learning to select some data-driven network distances. And it relates to the literature of uncovering latent heterogeneity, particularly using k-means as a clustering algorithm in panel data. So, and heterogeneity in slope coefficients or in fixed effects. But again, the key difference here is that in this literature, we are interested about unilateral memberships that, let's say, there is a kind of fixed effect, and then country A and country B and country C has they have the same fixed effect, while in my case, it will be that countries A and B have a certain covariance, and then countries C and D have the same covariance. So it's about pairwise relationships, which is a little bit harder to deal with. And in terms of the procedure that I propose, there already are graph theoretical papers that are helpful, not just to, well, the method is not purely a black box method. It is possible to think about consistency. So let me start with the framework. Consider k entities indexed by the set Vk from 1 to k. And each entity is given a random variable xk, x small k for the entity and capital K for the size of the network. Those I call entity characteristics. So those are single random variables. Then those entities are assumed to live on a random graph, gk, which consists of a set of vertices, which is the same as here. And there is a random set of edges. And then the network is defined as a pair of the random graph where the entities live and a vector of those characteristics for the entities. Now let C be a set of classes or network lags more intuitively, because you can see time series stationarity as a separate case of all this, because we can imagine a path graph and then compute the usual distances on a graph. So it is somewhat convenient to think about those classes that I will mention in a moment as network lags. So a classifier, which I denote by C, is any graph statistic by a varied graph statistic assigning a class to any pair of vertices. And here are 3 examples. So first, we could say that we're interested in the number of common neighbors between I and J, or the length of the shortest path between I and J, or the absolute difference of their degrees. And then the main definition is that I say that a network is said to be covariance C stationary if this classifier C, which can be, well, for a moment anything, is such that we have the following. So covariance between 2 entity characteristics conditional on the whole graph is equal to the covariance conditional just on the class of those 2 entities. So again, relating to time series, it would be that we don't care where the 2 points in time are, all we care is the lag in time. And here also we don't care where exactly in the graph those 2 entities are. What we care about is their distance or certain measure of the 2 of them relative to the whole graph. And then the gamma here is the autocovariance function, again very much relating to time series, which we are interested in estimation. Now to summarize the results of asymptotic theory, let me first define a couple of things. So let's pick class C, which could be, for instance, just a natural number 1 for the case where we care about the distances, the usual distances. So class 1 would correspond to all the pairs that are connected, that are neighbors. So then QC is a set of such pairs of entities ij that have this class C. So this corresponds to, in a way, n, when we have 1 over n in the sample mean. So that's our subsample that we will be interested in. And let's define one event, saying that the class size, so that's the cardinality of this set, that the class size is positive. So then we may want to estimate at least the following things. So first, we may be interested in the conditional mean of x's, and it's conditional on the class of the entity with itself. So for instance, this classifier may be the number of neighbors. So the more neighbors I have, possibly the higher my mean is. We may want to estimate this mean depending on the class, and on the other hand, the mean may be constant on the graph. So that's simpler. And the estimators are as you would expect. So for instance, for the constant mean, it's just the sample mean where we average all the k entity characteristics. And if we are conditioning on the class, then again, we sum all the x's that are from this class. And relating to the next slide, notice that here we have the subsample size, 1 over cardinality of QC. And as I said before, in the framework, the graph is assumed to be random. So the denominator here is random, and that's what gives some of the fun challenges. And something very similar happens with the autocovariance at a certain class C. We sum over all the pairs, ij. Here I center them with the constant mean, and we divide by the same covariance class. And then to summarize the results, the mean results, both types of mean and the covariance are consistent in L1 norm, and also we have this central limit theorem for the mean, for the constant mean. Now, one of the more interesting and simpler and more representative assumptions is the following one on the class size. So let qk be the quantile function of the class size squared. And we are conditioning on the when that the class is non-empty, that we have at least something of this type of covariance. So then the assumption is as follows. In part 1, we have that the class size has to diverge in probability, which is somewhat intuitive, makes sense. And you can also notice that it is necessary and sufficient for the mean of something like 1 over n to go to 0, but it would be just sufficient for the expected class size to diverge. So what it means is that we don't want to have possibility as the in-network grows, as the class grows, well, as the network grows, we don't want to have a possibility that this class that we are interested in sometimes is very small, that we have just, well, infinitely often that it is very small. So in other words, this first part requires the distribution of the class size to be shifting to the right. And the second assumption is that the second moment of the class size should be of big order for any quantile of the class size squared. And in simpler words, that would mean that the first quantiles or the left tail or the very beginning of the distribution should be close to the mean, which again relates to the first assumption that we don't want to have small class sizes. So the right tail may be there, may be longer, but we want the distribution to be somewhat concentrated. So that's the main message from the asymptotic theory. Now let me, in one slide, explain what I mean by network dependence counterfactuals. So let G star X star be an observed network realization. So we have the whole graph and we have all the network entity characteristics. Then if somehow we do know which classifier we should be using, then we can estimate the autocovariance function gamma as before, with the same estimator, and we can estimate the whole covariance matrix for the whole graph. Now let's take another graph, now just a graph, not a network, G tilde, and let it be some hypothetical graph of interest which we choose. And in many cases, it will be some slight change relative to the G star. For instance, we add a single vertex, or we remove a single vertex, or 2 or 3. So some small change. And now this notation maybe is not the best, but let me explain it in words. So under network stationarity, if the class of I and j from the initial graph that we do observe is the same as the class between k and l entities in the hypothetical graph, then if we have the same network process, if we assume that both graphs come from the same network process, then we can use the same autocovariance estimator, the same gamma hat, where gamma hat is obtained using only the G star and X star, only the observed graph. And we can go further. So if we assume that those two graphs come from the same network process, and that this classifier C does give us C stationarity, then we can also estimate the whole covariance matrix of this hypothetical graph, and we can estimate functions of this whole covariance matrix using this gamma hat that is obtained using only G star and X star. So in particular, we are doing all this without observing the corresponding axis. So again, to go over this again, we do observe a full network, and we assume that there is another graph that comes from the same process, but we do not assume what the hypothetical axis would be, just that the network process is the same. And if that's the case, we can use the same autocovariance function estimator. So that's a rich feature of networks, because as I said, if we change a single connection, it does affect a network, and we can exploit that if we believe that after the single change, the autocovariance remains the same. Of course, that is a strong assumption. And if we make this assumption, then possible applications would be in prediction, in proposing measures of influence and robustness of networks, extracting graph weights, and so on. And now let me go to the last part of machine learning. So before I proposed 3 examples: the number of common neighbors, the length of a shortest path, the difference of degrees. So those are somewhat simple classifiers, and it's very likely that a proper classifier is going to be known in very few situations. For instance, in transportation networks, we may care just about the distance, but typically there probably will be no clear choice in some complex social network what we should be using. And explicit classifiers like those 3 examples, they tend to be just about structure of the graph, how many neighbors I have and you have. So and well, in particular, if we have the same neighbors, or comparing the number of our neighbors, or proximity between us, while in the real world networks, because of their complexity, we actually may care about a mixture of this, and we may prefer something that relates to black boxes. So then the goal would be to develop a class of data-driven classifiers that possibly gives us this mixture. But then a challenge is that we need to handle pairs of vertices, because we want to say that, okay, this pair of vertices has the same covariance as another pair of vertices. So, and that's somewhat more challenging than clustering individual nodes. And as I said, what may seem to be helpful is to map pairs of vertices or vertices to a space that is amenable to clustering. So for those who are not very familiar with graph embeddings, here's a very quick illustration. So on the left, we have a graph. So forget the colors. Imagine that we don't have colors. We have a graph, which is not a geometric object. We could revisualize it in whatever other way. And then using a graph embedding algorithm, we can map it to the graph on the right, where now every node is assigned to some vector in R2. And in this case, the embedding is for vertices. And well, I will be interested in pairs of vertices, but let's say if our goal were to cluster pairs of vertices, you can see that they are clustered relatively nicely. So to summarize one of the procedures that I propose, let a vertex embedding algorithm be given, and then edge learning operator star. I will come back to that in a moment. Then let's also say that we have a clustering algorithm, and we choose the number of embedding dimensions and the number of clusters, so D and N. So, well, because of time, I can't give you a nice overview of the embedding algorithms. And for clustering, for the theoretical purposes, most likely I will be focusing on k-means, because the papers that are available with theoretical results and papers in econometrics are very much focusing on that too, because of the nice theoretical properties. So then as to obtain a classifier, what we may do is something very straightforward. So first, we use a vertex embedding algorithm to embed each vertex, each node k, to some vector pk in Rd. Then I set another vector pij, so that this will be my edge embedding, and I will learn it, I will construct it by using vertex embedding. So one of the reasons for this is that vertex embeddings are simply much better developed. They work much better, and there's much more interested in that. And this kind of procedure of combining vertex embedding vectors into a single one is also something that is used. So in this way, we obtain well, I should not say an edge embedding, because in this way you may think that I'm interested only in edges that are present, but actually I want an embedding for all the pairs of vertices. So then, given those vectors for all the pairs of vertices, I just cluster them into n clusters and define the resulting classifier C as follows. We say that entities I and j have class C if their vector belongs to cluster C. So now some comments about this. The larger D is, the larger the embedding dimension is, the more accurate it's going to be, because the graph itself is something very high dimensional, although choosing a larger D has some other disadvantages that I'm not going to mention now. Then for the edge learning operator, popular choices are the average, element-wise L1, L2 norms, and in particular, what appears to work well is this Adamar element-wise product, which I also use in the paper. Then larger values of n are safer in a sense that if we have a single large class, the same covariance, then it is fine if we split it into two, because we will still be estimating it consistently. Now, on the other hand, if we have two classes, let's say two clusters that actually correspond to two different covariances, if we are going to choose to find fewer clusters, and we are going to cluster two covariances into the same one, that will be underestimation. So it's not really that we want to recover the clusters correctly and to interpret them. We just want not to choose too few of them. But again, choosing more clusters again has some disadvantages. Now, an obvious drawback of all this is potential loss of interpretability, as in many machine learning algorithms, because we may get the classifier will have values 1, 2, 3, 4, and so on, and we will not be able, in many cases, to interpret those values. Now, the benefit is that in this way, we are able, in most cases, to use directed and weighted graphs, because the embedding algorithms are typically able to handle those. Then this procedure also could be extended to network dependence counterfactuals, meaning to measure those counterfactual covariances with the data-driven classifier. Then the key challenge in proving consistency is about this edge learning operator again, particularly if I want to prove consistency with the Hadamard product. So that creates some challenges. And I also have some applications with adjacency spectral embedding, and comparing to typical classifiers, the explicit ones, it does have some promising results. So I think I'm right on 25 minutes. And to conclude, just a reminder of the 4 parts and the results there.
Great. So yeah, you're on time. And no questions from the audience. I guess your stuff is too dense. Great. Actually, now shows up some question. Andrei, do you want to ask a question yourself? Do you want to ask a question yourself, or I ask a question on your behalf?
Do you hear me?
Yes, yes, please, go ahead.
Yes. I just wanted to ask, basically, as there is no other question, you were talking about network dependence and network stationarity. But definitely, as far as I understood, your analysis is based on, one could say, cross-sectional static network. Could this be extended to temporal dynamics, to stationarity also in dynamic perspective? Because there is literature on similar quantities and similar relationships there. I linked it in the comment. Thanks.
Okay. Thank you for your question. Well, we could do this, we could cheat a little bit. So for instance, if we have one network at time 0, another network at time 1, we could imagine one large network where you see 2 of them and they are possibly separated. Again, it depends on how we want to model the network, the time dependence. We may introduce new classes that correspond to being at a different time. So you could play with this framework. You could work with that, although it is not designed for that. Let's say it's more for just a single observation of a network. But that's something that is relevant, and in some ways it would be even better.
Okay, so maybe I ask a question then, and so your key assumption is the stationarity, right? Of the dependence. I guess it depends on, when you're talking about counterfactual, I think it really depends on what you are interested in, right? I would think about each of us, we probably have different kinds of network dependence, right? Depends on your professional work or your family, this or that. So it will be quite different dependent structure, right? So because I was not clear what's the objective interest here.
Well, so one example would be that if, for instance, we have a village, so the data set with the microfinance in Indian villages. So there was this information diffusion where villagers talked about the microfinance program with each other. So there, as to measure covariance between their decisions, you could, for instance, think about how many common neighbors they have. Meaning that if me and you have just a single common neighbor, then the covariance possibly will be low. And if we have 6 neighbors in common, then possibly we have some similar opinions, share some similar information about this microfinance program, and our decisions may be somewhat correlated. And in the paper, I use this exact data set, and I do see this in this autocorrelation graph. I do see that the more common neighbors you have in this data set, the more similar the decisions are. So yes, it definitely depends, and that's one of the reasons why I introduced this generality, the general function C, as it does depend on the case. That's exactly what I was arguing at the very beginning.
Okay, good. Let me see, you have one new message. Oh, okay, one go. One, do you want to ask a question? One. Okay, maybe I ask his question then. He asked me, where is your paper posted? Couldn't find your web page. Sorry.
Right, so as I mentioned, this relates to multiple papers, and at least the main one on the framework and the symbiotic theory should be in my website soon, in let's say in a month or so.
Okay, great. So thanks for the very interesting talk and the interesting news way of thinking. And yeah, so now perfect timing. Let's move to the next speaker. Andrei is also talking about social network. So Andrei graduated from Princeton, is now assistant professor at UCL.
Oh, so can you hear me? Can you see the screen?
Yes.
Okay, great, perfect. So first I want to thank the organizers for providing us with such a terrific opportunity to present our works. in front of such audience. It's a great initiative. I think we really appreciate it. Thank you. So I'm going to talk today about identification estimation of network models with flexible forms of unobserved heterogeneity. And of course, it is well known that it's important to properly account for unobserved heterogeneity in microeconometrics in general, as well as in the context of analysis of network and interaction data in particular. And for example, the standard additive two-way fixed effect framework is routinely employed to control for unobserved heterogeneity in networks. So its numerous empirical applications include, for example, a comparison of firms and workers fixed effects in the wage regression context, or exporters and importers fixed effects in analysis of the international trade network data. Okay, so also at the same time, its theoretical properties are also relatively well understood. Correspondingly, one of the most standard models used to analyze network data is just the standard linear network regression model with additive fixed effects. So in this model, Yij stands for the outcome of the interaction between two agents, I and J. Wij is a collection of pair-specific covariates. So beta naught is the parameter of interest, which you want to estimate. Xi I and Xi J are the unobserved fixed effects. And epsilon ij stands for the idiosyncratic error. So for example, you might think of this model in the context of the international trade network, then Yij would be some measure of trade volume from export volume from country I to country J. Wij would collect such variables as, for example, geographical distance between countries I and J, as well as a collection of dummy variables indicating if they have a common border, legal system, and so on. Xi I and Xi J could be interpreted as the exporter and importer fixed effects in that context. Okay, so even though this additive fixed effect framework is widely used in practice, unfortunately, it's not flexible enough to capture more complicated forms of interactive unobserved heterogeneity, which are likely to appear in many settings. And specifically, one might find this structure particularly restrictive, since we know that the agent's observed characteristics typically enter this model in an interactive fashion. By this, I mean that Wij, okay, is often, the vector of pair-specific covariates is often a function, a non-additive function of agent's observed characteristics. So for example, geographical distance between countries I and J is clearly not an additive function of their geographic coordinates, right? Or in context of social networks, you might think of homophily or assortative matching based on agent socioeconomic characteristics such as gender, age, race, and so on. And correspondingly, it's very reasonable to expect that the agent's unobserved characteristics, which are their fixed effects, might also enter this model in a more complicated fashion than just purely additively. So in social networks could be homophily based on unobserved. Okay, and of course, failing to properly account for this possibility in particular or any other non-trivial form of interactive unobserved heterogeneity in general is likely to result in inconsistent estimators, erroneous inference, and misleading policy implications. So I address this issue in my paper by allowing the agent's fixed effects, again Xi, Xij, to interact via some unknown coupling function G. So importantly, this coupling function G is an unknown object, and my approach is completely agnostic about the structure of this function G, and also about the dimensionality of the underlying fixed effect. Okay, so this flexible approach is in contrast with most of the existing ways of dealing with interactive fixed effects in networks, or more generally in two-way models. So one of the most common approaches is to explicitly specify the functional form of this function G. Okay, factor structure is really popular. Or some papers treat this function G as a non-parametric object, but at the same time, impose additional assumptions on its structure. Say it's increasing in both of it scalar arguments. So the more, the better again. So at the same time, we know that networks are really about assortative matching and homophily, and it's important to account for this possibility. And my flexible structure allows me, for example, to cover non-parametric homophily based on unobservables, in which this function G would be decreasing, some decreasing function, which depends on the distance between agents' latent characteristics. So in this model, agents which are similar in terms of the unobservables going to generate higher surpluses on average than those agents which are distant, and so I can allow for that in particular. So just before proceeding, let me briefly outline the main results of my work. So specifically, I focus on identification and estimation of this single index model. So it's general than that model you've just seen before. And it's important that I allow for the presence of this known and invertible linking function f in order to make sure that my approach, my model is flexible enough to cover most of the existing nonlinear network models. For example, if your y is binary, f could be the standard logistic CDF, and that would correspond to a logic network information model. Or if f is exponent, then that would correspond to standard Poisson regression. Okay, so in this model, I establish identification of beta node, which captures the effects of the observables, right? And I also establish identification of the value of this function g xi xij for all pairs of interacting agents. So second, I construct a number of estimators of this parameter of interest beta node, the actual consistent, and I derive the rates of convergence. And then I also want to mention that as a byproduct, I also provide additional generic identification results. So specifically, I demonstrate how recent developments in matrix estimation and completion literature could be leveraged to substantially facilitate our identification estimation analysis of complicated two-way structures with rich forms of unobserved heterogeneity. And by doing that, I provide a foundation for establishing results in other contexts, such as large panels, for example. Okay, so first I'm gonna talk about my identification strategies, but before jumping, let me briefly introduce the framework in a formal way. So I'm just gonna discuss the simplest case. We observe a network which consists of n agents, and they have observed and unobserved characteristics x's and xi's, which are also called fixed effects. So in the simplest case, I assume that we observe the outcome of the interaction for all pairs of agents in that network. And the model I study is essentially in the simplest form is a generalization of that network regression model, but in which fixed effects are allowed to be coupled via some unknown function g. So again, just for simplicity, I'm going to talk about undirected networks, so outcomes, covariates, g functions, idiosyncratic shocks going to be symmetric. Okay, but this is really not restrictive. Exactly the same insights apply to directed networks and general two-way models. So, and to facilitate analysis, I'm also going to make one more assumption that, Wj, the vector of pair-specific covariates, is a function of agents' observed characteristics. For example, the geographical distance between countries I and j is a function of these countries' geographic coordinates. So this is standard in networks. Then the data generating process is formalized as follows. We assume that agent characteristics are ID and conditional on those characteristics. These idiosyncratic errors, epsilons, are independent from each other and have conditional zeroing. Okay. So in this framework, I'm going to study, at least I'm going to start with studying identification and estimation of beta node, again, which captures the effects of the observables. In the context of the so-called large network asymptotics, which takes the size of that network to infinity. So, and specifically, my identification strategies are based on the following observation. So, suppose I am able to find two agents, I and j, with exactly the same values of the unobservables. So now let me take, I have these two agents, let me take any other third agent k, and let me compute the difference in these outcomes. Since agents I and j are identical in terms of the unobservables, this part associated with g functions going to be difference out from this equation. It's no longer there. And consequently, you could potentially identify and estimate beta node by just considering this regression. You just regress the difference in the outcomes on the difference in the covariates, and you're done. So of course, like an important remark, these pairs of agents you match should not only be identical in terms of the unobservables, they must be necessarily different in terms of the observed characteristics axis, because otherwise imagine like that part also going to be gone from this once you do difference, and that part is also gone from this equation, and you wouldn't be able to identify beta node whatsoever. So just to recap, as you can see, the problem of identification and estimation of beta node in this model can be reduced to the problem of finding pairs of agents with the same values of their unobservables, but with different values of their observed characteristics axis. And now I'm going to talk about how this can be done. So to make further progress on that, let me introduce the following notation. Let Yij star stand for the error-free outcome of the interaction between two agents, I and J. So specifically, I mean, essentially this is the same Y, but without error. I just got rid of this epsilon. Or in other words, this is the conditional mean of the interaction between two agents, I and J, given their characteristics. That would be the mean if you observe those agents interacting zillion times. Okay, so now I'm going to build on these error-free outcomes and construct the following pseudo distance between any two agents, I and J, which is equal to the minimum over beta of the following conditional expectation. So I take the minimum over beta because true beta is unknown, beta naught is unknown, okay? And this expectation is conditional on agents I and J characteristics because these are treated as fixed. I compute distance between them, okay? So what is random here is this third agent K, okay? That third agent K is treated as random, and the expectation essentially is taken over its characteristics, over characteristics of that agent K. So the question is, why do I care about this pseudo distance? It turns out that it is informative. It is actually informative about how close these agents I and J are to each other in terms of their unobserved characteristics. So specifically, you can see that if xi equals xij, then this difference associated with this G function is also going to be gone. And by choosing beta being equal beta naught, you can ensure, right now, you can ensure that this pseudo distance is indeed equal to 0. And under a fairly standard rank condition, this becomes an if and only if statement. So if you know that pseudo distance between two agents, I and J, is equal to 0, then you also know that those must be identical in terms of their unobserved fixed effects. Okay, so that's the idea. However, now you can reasonably claim, well, your pseudo distance is built on some hypothetical objects, Y stars, which are not available for the researcher. So it's not actually clear if you can make any use of that pseudo distance. So now I'm gonna talk about how this problem can be overcome. It turns out, so okay, I want to demonstrate how this can be done and how yet we can exploit this pseudo distance to match agents with the same latent characteristics and different observables. So it turns out that a nice, simple solution exists in a special case when the regression idiosyncratic error is conditional homoscedastic. So sigma squared standard stuff, sigma squared stands for the variance of your epsilon, in this case, conditional variance of epsilon. So what was the problem with the previous pseudo distance? Kind of nice that it's built on those unobserved hypothetical outcomes, Y stars, and I have no idea what those are. I don't observe them in the data. So let me consider a feasible analog. So now I'm just going to consider a feasible analog of that quantity D squared, denoted as Q squared, in which I just throw in plain Y's. So no more Y stars, I just throw in plain Y's. Now on the observables are here, right? On the observables are here, and this expectation can be estimated by its sample analog. So simple as that. So now the second line is a simple manipulation. Essentially, this is the definition of Y star. Y is equal to Y star plus epsilon, right? This is that's what it says. And the third line now leverages conditional mean independence of epsilons from the characteristics. You can now, the idea is to split epsilons from that part which I'm interested in. So you can see now, okay, the first term here is just the pseudo distance. This is the object I'm after. This is the object which helps me to find agents with the same latent characteristics. And the second term is associated with the variance of conditional variance of my epsilons, which is under the conditional homoscedasticity assumption is just a constant 2 sigma squared, which is the same, importantly, the same across all pairs of agents. And as a result, I just demonstrated that Q squared equals D squared plus 2 sigma squared, and 2 sigma squared is a common constant, and consequently Q is minimized whenever D is minimized, and you can do matching in this homoscedastic model. You can do matching of agents based on that quantity, okay, which can be estimated from data. Great, but unfortunately, this argument wouldn't apply in the case if your conditional, the conditional variance of your epsilons would be a function of agent's characteristics. And of course, this homoscedasticity requirement is restrictive and unrealistic, unrepresentative of many empirical settings, and we want to relax it. So now I'm going to demonstrate, I'm going to discuss how this strategy can be generalized to handle models with general forms of heteroscedasticity. So specifically, this identification scheme becomes a little bit more involved. Okay, there are multiple steps there. The first step is about identification of agents with exactly the same values of both x's and xi's. I'm not going to talk much about this step because this is not original to this work. So people knew that it's actually possible to extract information from network, using some similarity, a certain concept, similarity distance or other related objects, and find agents with the same characteristics. So, for example, I guess this similarity distance originates from the work of Lovash and co-authors on topological properties of graphones, and Eric Auerbach pioneered that approach in econometrics, where it's also used in statistics in the context of non-parametric graphon estimation. So, however, now important point that I want to make, this is not enough. So people knew how to do that, but this is not enough to disentangle the effects of x's and xi's. And that's what I do in this paper. In this paper, I show that you can actually disentangle the effects of the observables and unobservables without specifying how these unobservables interact with each other. This is not enough to identify beta node, because you wouldn't be able to disentangle the effects of x's and xi's in this case. So the second step, so it turns out that the first step can be exploited to identify these unobserved error-free outcomes. So specifically, I demonstrate that this object is identified, can be uniformly consistently estimated. So you kind of know the left side of this equation, you know Yij star for all pairs of agents. And this, what does it mean for us? So it means that these error-free outcomes can be treated as effectively observed, and it immediately brings you back in the most extreme homoscedastic setup with no idiosyncratic errors at all, right? And now, since you're back in the homoscedastic world, you can apply my argument, you can apply the same argument to find agents with the same values of xi's and different values of x's, and this is key. So this allows you then to disentangle the effects of observables and observables, because you now have variation in x after controlling for xi, and beta node can be identified from this pairwise difference regression. So finally, before I proceed, a remark that identification of pair-specific fixed effects also comes naturally here. Since I know Yij star and I know beta node, then I can just, I just subtract the contribution of the observables, and I know and can uniformly consistently estimate all these pair-specific fixed effects for all pairs of agents, which is especially important in nonlinear models, so they can affect partial effects. Now, a few words about this result, identification of the error-free outcomes. So it turns out that this problem is closely related to the classical matrix estimation completion problem, and so this comes naturally because a network is a double array structure. So in particular, the network model I study, as as virtually any dyadic network model, belongs to the so-called class of latent space models studied in G, for example, in which Yij star is some unknown transformation of the agent's latent characteristics. And it's a great foundation for us because these latent space models have received certain attention in the recent machine learning and statistics literature. So in particular, different papers construct estimators of those error-free outcomes and establish their consistency in terms of the mean square error, or if you collect them in matrices, in the Frobenius norm. So this is unfortunately not sufficient in my context, because what I wanna demonstrate, I wanna show that if your network is large enough, then you can back out all these Y stars at the same time, which gonna formally prove identification. So, and to do that, I construct a different estimator building on the approach of Jean Levin and Zhu, but I construct a different estimator and I establish its uniform consistency of matrices. That's going to be consistency in the subnorms. So, which solves this problem and formally shows that indeed Y stars can be treated as effectively observed and delivers that identification result. So now I'm just going to quickly talk about estimation. So my estimation strategies are essentially two-step estimators. All the two-step estimators. The first is to estimate those underlying pseudo distances. So somewhat simple under conditional homoscedasticity, more involved in the general case because it requires you to pre-denoise these error-free outcomes. And the second step is all about finding agents similar in terms of their unobservables based on those pre-estimated pseudo distances. Now, an important remark, of course, in finite samples, you can never find pairs of agents with exactly the same values of the unobservables, right? And yet in a network of a growing size, you can find some pairs of agents which are going to be increasingly similar to each other in terms of their size. And as a result, this bias introduced by imperfect matching is going to vanish. And specifically, I consider the following pairwise difference estimator, which essentially combines all of these pairwise difference regressions with different kernel weights, in which this bandwidth essentially controls how close these agents I and J could be to each other in terms of those pseudo distance. So if they are close relative to, if that pseudo distance is somewhat similar to that bandwidth, then those pairs of agents are probably somewhat similar in terms of size, and they're gonna contribute. They're gonna have a non-trivial contribution to estimation. So it's it's an econometrics talk, and I want to show at least one theorem, at least quickly. So I formally established the rate of convergence for that estimator under certain high-level conditions first, and it turns out that important condition is that during your first step, you can uniformly consistently estimate all of those pseudo distances. And it turns out that this rate of convergence also affects the rate of convergence for beta hat. I'm interested in her beta hat, not those distances per se. And you can bound the rate as follows. So here, this bandwidth squared captures the bias introduced by this imperfect Xi matching. So as bandwidth goes to 0, this bias disappears eventually. And the second term effect essentially, captures how this uncertainty from the first step propagates to the second step estimation of beta. So that's it. And I derive, I also verify this condition, I derive rates for my estimators in different settings. So now, before concluding, I just want to show you quickly a simple Monte Carlo experiment. So it's going to be a homoscedastic model, which features homophily based on both x's and xi. So beta naught is -1. Okay, and I allow my x's and xi's latent characteristics and observed characteristics to be correlated. And I'm going to compare performance of the following estimator. So the first is just the standard additive fixed effect estimator, ignorant about this latent homophily based on xi's. The second is my kernel based estimator you just saw. And the third is that one nearest neighbor is itself like one nearest neighbor estimator. So what's going on here? So non-surprisingly, if your x's and xi's are correlated, then the standard fixed effect estimator suffers from the emitted variable bias. It's heavily biased. Whereas my estimator, beta hat, it effectively removes the bias even in networks of a very reasonable size. Okay, so which is nice. And another remarkable thing, even if emitted variable bias is not a problem, even if rho is equal to 0, you can see that my approach is, it's really surprising at first. My approach is so much more accurate also in terms of the standard errors. But this is because this latent homophily is a heavy determinant. Xi's are a heavy determinant of the outcomes. And for the fixed effect estimator, this becomes a part of the unexplained error. So this is unexplained variation. And it turns out that my estimator, which effectively removes, right, it effectively differences out these unobservables at the cost of reducing the sample size. And it turns out that doing that at the cost of reducing sample size is beneficial in terms of accuracy. So I guess that's where I'm gonna stop and briefly conclude. It's a long paper, so I also have extensions to more sophisticated models like that single index model I mentioned. So you can also identify, so all these results are not due to this special linearity in beta naught or functional form. You can identify non-parametrically that function H which captures the effects of the observables as long as you have the additive separability in x's and xi's. Okay, and I also have an empirical application, an empirical driven simulation study in which I study homophily effects in social networks using this famous Facebook 100 dataset. So especially going to be gender effects in a logit model. So it's a nonlinear and heteroscedastic model clearly, which I also estimate. So yeah, I guess that's pretty much it. This paper is mostly on identification and estimation. Inference is not yet a part of the paper. I think it's objectively hard, if not completely impossible. But at least in simulation, subsampling without replacement works really well, and that's one of my hope how you can also do inference in this model. Okay, I guess that's pretty much it I wanted to cover today. So thanks a lot.
Great. So you have two questions. Is Andrei, you want to ask question first? Andreas, do you want to ask question first?
Okay, thank you for allowing me again. I just wanted to ask you, you had a kernel type estimator on slide 12, and you mentioned Epanechnikov kernel as possibility. How do the properties that you showed of this estimator depend on different type of kernels that could be possible to use? Thanks.
So yeah, I don't have a slide with technicalities here. Yeah, it depends on the kernel, and so here there are hidden constants which gonna depend on the properties of that kernel. I mean, I think the important part that kernel should be, as far as I remember, that kernel is supposed to have bounded support. So this is important to get these rates. That's the first thing. And second, I guess this kernel is also supposed to be Lipschitz continuous. Yeah, these are the most, the restrictions, the main regularity conditions imposed on the kernel for me to get these rates. And of course, once you bound the variance and bound the bias, other properties of the kernel also show up. But I don't do any analysis. I don't have much to say about how you should choose your kernel other than that.
Great. So you have two more questions. Arthur, do you want to ask your question?
Sure. So given that you can identify Y star, can't you use higher moments to either get greater efficiency of beta or to provide over-identifying information for specification testing?
I see. So, so the question is if this model non-parametrically identified, right? And so because if it is, we could then turn this into a specification test. I see. Is that the question? If the model is non-parametrically already identified, and now we can run a specification test as a result?
Well, it's just that you have more identifying information than you're using. If you get
sure, but for me, it's still not clear. It's not immediately clear that the model is non-parametrically over-identified. Specifically, if you, yeah, you could probably test some of the assumptions, but since that step, right? Like I can't, even if you can do it, I can't really think of a formal. So this is definitely an interesting question. I thought about that at some point, but coming with an actual test, and critical values for those tests could be pretty hard. In fact, you could probably do some diagnostics, but it's hard to formalize that because it's based, once you think about sampling variability, it's based on that pre-estimation of these error-free outcomes, and it's very little is known about those properties of those machine learning first step estimators. We only know some rates of conversion in terms of the MSE, but trying to figure out actual distribution for any sort of statistic to actually run a formal test of over-identification in this model. I honestly don't think it would be feasible, even if the model is not parametrically over-identified, which I'm not super sure now. I mean, it depends on if you put additional restrictions, that's for sure. Yeah, and
so will be future work. So a lot of, right? So one more last question. One go. Do you want to go?
Oh yeah, thank you. Yeah, nice talk. Could you go back to slide 7? The question I have in mind is that so if this unobserved heterogeneity C are actually a scalar, then I would think about like conditioning on them being equal, we still have variation in X. But if I sort of really think about C as really general, let's say like includes even this person's DNA sequence, like personality, IQ, social, economic, and unobservables, then how should I think about the possibility of having the observables being further unequal, conditioning on the equality of this non-parametric unobservables?
Yeah, sure. I see where your question is coming, and it's important, right? Like that's one of those assumptions which let me disentangle those effects. I have this additive separability, and conditional xi. I wouldn't have. Of course, I would be in trouble with conditional xi if my xi is everything, then once I condition on xi, I wouldn't have variation in x, and I would be in trouble disentangle those effects. So this is a fundamental assumption. Okay, so I should have variation in x conditional on xi.
Great. It's okay. Future
So
work.
so this is no. I mean, this is an assumption. I have separability in those observables and non-observables, and I should have to get non-parametric. Forget about functional form, like here. Forget about linearity. To get a non-parametric identification result, I need variations, and that's what I need. I need variation in x conditional on xi. Otherwise, what can you do about that?
Sure. Yeah.
Great. So let's thank all the speakers for excellent presentation. And I think also thank the questions. Now just announcement for 2 weeks from today, we're very happy to have Rafaela talking about identification, inference, and narrative restrictions.